so these conditional inferences we can exploit in an algorithm called variable elimination. Which is nothing but the application of dynamic programming when we do repeated inference, that is for inference in such graphical models. So consider again our model. And let's say we're interested in the probability of there being a bomb given that our X-ray showed something. So our X-ray showing something we can again indicate by shading this node in which we make an observation. And the conditional probability of B given X is the same as the joint divided by P of X. And so we need to make two computations here for the numerator and for the denominator. And let's start with the numerator first. So the joint of P and X is obtained by marginalizing over the variables we're not interested in. And, well, if I just insert naively the joint probability, I obtain the following. So I'm just inserting here the factorization for the joint. And note that not every term here depends on K and C, so I could rearrange my sums. But before rearranging, I will have a total of 4 summands here. And each one has 4 factors. Or if I count operations, then for my 4 summands, I have a total of 3 additions. And in each summand, I have 3 multiplications. And now I can rearrange my computations. So for instance, P of B, I can pull out because it does not depend on either summation. And then I let my summation over K go only over the single term that actually depends on K. And I still have the summation over C. Okay, if I count again, now here I have 1 addition and 1 addition, makes for a total of 2 additions. And here I have 2 multiplications because I have 2 summands. 3, 4. So a total of 4 multiplications. And again, these differences here between factorizing out what can be factorized out or not, they can become extremely large for bigger graphical models. Now we can, if you look at these terms here, we can think of them as messages. So here I would have a message phi that is obtained by integrating out C, and the remaining variables in its scope are B and X. Here I have a message that was obtained by integrating out K, which still depends on B. And here I have a message only depending on B. So these are messages that the various graphs are sending in their opinion about what the joint probability here of B and X should look like. And these messages can now be arranged in a meaningful fashion. So I can associate these messages with the edges of a clique tree. Or it comes under many names. It's also called the join tree or the junction tree. So here we have compound objects like this one here, depends on X, B, and C. And this is now sending a message where variable C has been integrated out, so it only depends on B and X. Similarly, we had a message here from a domain that was depending on B and K. And in this message here, K was integrated out and it hence depended only on the state of B. So the variable elimination algorithm has its name because we are eliminating one variable at a time. Okay, so so far that's not of particular interest, but now look if we want to compute also the denominator. So this was the numerator, and now we look at the denominator, namely P of X, which by definition can be written as follows. And now I can insert here what I found before. So I could say that this is the sum of the following factors: phi of B, phi k of B, and phi c of X and B. And I can say that this is now a new message in which B has been integrated out and which only depends on X. And I can hence extend my graph here a little and say that to compute the denominator here, I'm sending this additional message phi B of X to an element of this junction tree which now depends on X only. And that means we could use these same factors that were previously computed to obtain this term here. Or, in bigger graphical models which involve, assuming that our clique tree continues here, let's say it fans out on the right-hand side, the messages from the left-hand side would be the same no matter what we have here on the right-hand side. This is why I can reuse those messages and why I can reuse those computations. And this is why this is an instance of dynamic programming. So we are recycling, not in the sense of throwing away. So European recycling, not throwing away, but actually using again. We recycle the results or the computations from the computation that were required for the numerator. Well, and if you look at these equations, you see a pattern, namely, we always have a sum over a product, a sum over a product. Here again, a sum, summation, a sum over a product. And this is indeed why this is also called sum product variable elimination. And I'm going to, we've looked at a specific case, and I now want to write down the general algorithm. If you want to read up on this, there are a couple of good books on graphical models. There is, for some of the more fundamental relations, there is a book by Stefan Lauritzen from 1996 called Graphical Models. Then there is an unpublished manuscript by Jordan and Bishop. I think it's dated 2001. And you can hunt for it on the internet. It's called something like Introduction to Graphical Models, and it's sometimes cited in papers, but it's never appeared, unfortunately, in print. So it's probably one of the most cited unpublished books. Then there is Bishop's book on machine learning itself, 2006. And there's a new kid on the blog, which I really like. I have a screenshot, I think, of the webpage somewhere. Oh, here it is. It is called Bayesian Reasoning and Machine Learning by David Barber. And it's available in print. But it also has a homepage, which unfortunately was down this morning, on which you can get a PDF copy and on which you also find how is this called, advertisement code or something, which will give you a reduction if you want to buy the print copy here. And, well, importantly, I should mention the book by Koller and who's the second author? Koller and Friedman. Is it? Oh, I forget the year. 2000, could it be 9? Maybe. Near Friedman it is, yeah? I think, yeah. This book has everything. It has just one mistake, namely that it has everything. So it's encyclopedic, it's 1200 pages or so. So this is, this is the reference, for if you want to do research in this area, if you want to learn about it. My favorite of today would be either the Jordan book here or Barber. Okay, so here's the sum product variable elimination algorithm as presented in this book by Koller and Friedman. So this is Koller chapter 931. We have the following input: capital Phi, which is a set of factors; capital Z, which is a set of random variables that we want to sum out in our effort of marginalizing over them. And then we need some ordering of these random variables. It turns out that this ordering is actually important. And the output is a message or a factor phi star of y, where y are all variables except the ones which you have integrated out. I've integrated out everything in this set Z, and you're taking a product over all factors that you had originally. Okay, the algorithm goes as follows. So we have a counter from 1 until the size of the set of variables that we want to eliminate. And we build a new set let me call this phi of Zi. This is the set of all factors that involve variable number I, or set notation here, it's those factors which have the random variable Zi as an argument. And then we have a set of factors that I want to write as follows. It's the set of all factors that do not involve variable Zi, and then finally we have the actual sum product step. Namely, we have a new set of factors or an updated set of factors which is given by all those factors that do not involve variable I, as well as, now comes the sum product. So we have a sum over variable Zi, And we have a product over all factors in this set. So there it is again, the sum and the product. And the second part here, this is a new factor with zi integrated out. Okay, my loop ends here. And then finally I need to return the output, which is the product over all the remaining factors. So this is the output factor. And it of course can depend on more than one variable. If I have not integrated out all but one variables. And these output factors, well, depending on what group of variables you have in there, it can be interpreted as a conditional probability, but it need not be able to do that. So in a typical graphical model, when you integrate variables out, you sometimes get a quantity that you can interpret as a conditional probability, and sometimes something that you cannot easily interpret. So there's the algorithm. Any questions? On this algorithm? If you look at the cost of variable elimination, that will depend on the size of the largest intermediate factor that we generate. Because for these intermediate factors, we somehow need to store their probability tables, and the probability table involving many random variables will take us, will take a lot of storage. It does not at all matter for these tiny, motivating examples that I've shown here, but it does matter when you start to have thousands of states. So you can have, I said that this ordering matters, finding the optimum order, which gives you the smallest factors, is an NP-hard problem, but there are decent heuristics for this. So the cost of variable elimination is governed by the size of the largest intermediate factor. In general, what shape of tree we get, or what join tree we get, and the size that I've spoken about, depends on the elimination order. Finding an optimal elimination order It's unfortunately NP hard, or up to NP hard, but there are good heuristics such as the min-fill algorithm. These heuristics revolve around a so-called moralized graph. So what you have to do is the following. If you have two parents, then in the moralized graph, you remove the direction of the edges and you introduce an edge between all the parents that point to a particular node. Note that sometimes we might have, this is not biology, so we may have more than one, or we may have more than two parents for a particular node. So if we have, let's say if we have three parents here, then we would need to introduce an edge between each of these parents, besides the edges that we already have from which we have removed the direction. And what you see here, this is a set of nodes in which each node is connected to every other. So that is called a clique. And this is also a clique. And each clique has a factor, or is associated with a factor, that has in its scope all the variables in that clique. So the idea is to find a good elimination order such that you have cliques that are as small as possible. Moralizing. It's a stupid name. Moralisieren. Okay, so you have unmarried parents, and to legalize the kid, the parents should become married. And this is why it's called moralizing. Okay, not my invention, this terminology. Republicans, yeah. Yeah, or Mormons here. Huh? I mean, look how many parents we have. Oh. Okay. So one of these good heuristics is an algorithm called min-fill, and I don't want to go into detail here, but it minimizes the number of edges that need to be added to the induced graph after eliminating a node. Now this optimal or this size of the largest factor that you generate, let's say the maximum optimal size is small for polytrees. Polytrees. But it can become very large for arbitrary directed acyclic graphs. Directed acyclic graphs are abbreviated as DAGs. So what is a polytree? Let's say this here would be an example of a tree. And as soon as we now add an additional edge here, or sorry, an additional, if we have an additional root node here, this would make it a polytree, because we now have two roots, one here and one there. So for polytrees, this will work all right, but directed acyclic graphs can also have loops, like this one here. And well, this is a small loop, so the worst you will find here is a factor involving 3 or 4 variables. But when you have bigger loops or such situations, you might end up with very, very large intermediate factors. So again, I can use this tool to illustrate the induced graphs. So let's say I'm removing this observation here. And then I'll make a query. And you here see the original graph, which has already been moralized. So for example, Elle and Frank have become married so that they can, morally and legally engender Frank, and so on. Okay, so Cecily has been married to Brian so they can have Eric, and Kay has been married to Anne so they can have Gwen. So this is this moralized graph here. Now this is already a good heuristic. Let me not take min-fill, but let's use sequential. This is now in the order in which I've specified the nodes. I've probably started at the top left corner. And you see the biggest factors that we have currently are factors involving 3 random variables by the construction of the graph. And we can now start summing out. So apparently I started with Brian. And you now see an induced graph. So Brian has disappeared, but a new edge between Anne and Cecily has now appeared in this induced graph. And I can next sum out L and so on. I can keep doing this. And I hope to see some bad factors. Yeah, for instance, now we have a pretty big factor here, which involves 5 random variables. So this is, starting to be a big probability table. And that was the worst one that we had in order to compute this marginal result here. So those are the probabilities for John if we've made no observations and independent of what state the other random variables are in. So the biggest factor here comprised 5 variables. And we can now do the same, but with an optimum strategy. So this time I'm using, or not optimum, but using a good heuristic. So this time I'm using min-fill, and I'm summing out the variables one by one. And I get the same numbers, of course, but the biggest factor involved only 3 horses this time. Okay. So here, after the moralizing, each clique corresponds to a factor. And we're looking for small factors. Final comment, which still fits on this page. The value of the messages depends only on, let me call this the upstream structure and the direction in which the message goes, but not on why we need this message or where it is destined. So let me show again what I mean in this example here. So we computed for the numerator, this was the quantity of interest. For the denominator, we needed that. And I've sent this message here, and the message stays the same no matter if I need to go further in my join tree. Okay, and this is the very reason why they can be recycled, why they can be reused. So let me make a last comment here. Once such a tree has been calibrated, so it means all messages were sent to some root and from the root back to all leaves, then I can conveniently compute any posterior probability in the entire tree. I have then found the posteriors for all cliques. Okay, so let's have a break, and after the break I want to talk about factor graphs and message passing on factor